Hello, my name is Sakizloglou, and I will present to you our paper titled Towards Highly Scalable Runtime Models with History. I will start by introducing the systems with which we're concerned, namely systems with autonomous entities in highly dynamic environments, such as a smart medical environment, like the one depicted on the bottom right, where one can see numerous devices interoperating with clinicians to provide healthcare services to the patient. The complexity of these systems and their human-in-the-loop nature renders their maintenance, operation, and orchestration a challenging task. Self-adaptation, with its well-known MAPE loop, has been found to be a suitable scheme to automate the operation and orchestration of such systems. The knowledge base of MAPE for such systems, of course, have to handle abundant data and also mine them in a time and resource-efficient manner. In certain cases, such as the medical domain, the knowledge about history is also necessary for the operation and thus the adaptation as well. As an example from a medical guideline, from a real medical guideline, we present an instruction that reads, if there is a procedure, a drug should have been administered 1 hour before. The adaptation engine of a MAPE loop for such a system has to cater for this temporal dimension in data. And this exactly is our research objective: to enable time and resource-efficient adaptation that makes use of temporal data on the history of the system execution. We hold that this objective has 3 requirements. First, the storage of temporal data, that is, the representation of the system execution. Second requirement is the scalable querying of temporal data, that is, efficient retrieval of information from this representation. And the third requirement is about the sustainability of the storage solution of the first requirement. So how can this be maintained in the long run? How can all of this temporal data can be maintained in the long run? An overview of our approach: we present a 3-step querying scheme named in tempo from the distinguishing features of our approach, the incremental queries and the temporal requirements, the support for temporal requirements. And in tempo enables sustainable storage of execution history and scalable querying at runtime. We briefly present the foundation of our approach, namely rule-based self-adaptation, as it is presented in the reference on the bottom of your screen. It relies on the premise that architecture view is considered a suitable abstraction layer for MAPE execution. Then, architectural snapshots captured by a graph-based runtime model represent the knowledge base of the MAPE and are causally connected to the system. That means changes on the runtime model are reflected on the system and vice versa. Adaptation is then realized by adding and removing components and connectors in the runtime model. We briefly visualize this scheme. Here we have a runtime model representing a simplified version of the smart medical environment, as I described it before, which constitute the knowledge base of the MAPE. Then adaptation is performed by adaptation rules of the form event, condition, action, where an event triggers a check for a condition, and if this condition is met, then an action is taken. Conditions are captured via graph-based queries, model queries, and actions are captured by in-place model transformations. Queries are executed over the model during the analysis phase, and transformations occur during planning phase. Both of these phases interact with the knowledge base. In this context, a match for a pattern-based query in the runtime model is an adaptation issue. Queries are executed incrementally in that each run of the MAPE loop only new matches are found. Handling history is a particular challenge for analysis, that is the queries, which is where we focus in our work. We now present the in-tempo querying scheme, specifically step 1, which is about the storage of temporal data, which is also the first requirement of our research objective. We achieve the storage of temporal data via runtime models with history, where each runtime model element has a creation and deletion timestamp, symbolized by CTS and DTS respectively. We assume that monitoring provides system changes as time-stamped events, which are consolidated into a single runtime model with history. We briefly show how this works. Here we have a view with a top compartment and a bottom compartment. The top compartment shows the system the physical system, and the bottom view shows the runtime model with history. At time point t, an event occurs, a patient is added to the system, and this is reflected in the runtime model with history, where the creation timestamp reflects the time of the creation. The deletion timestamp is set by default to infinity, which in practice is the maximum value supported by the system. Then another event occurs at time point t plus 1. A pump is added and connected to the previously added patient. This is also reflected to the runtime model in history. Also, the time of the creation and deletion is captured by the CTS and DTS of the pump. I would like to note that we also support creation and deletion timestamps for edges, but I omit them here for presentation purposes. Then, at time point t plus 3, an interesting thing happens, namely the first pump, the previously added pump, is removed from the system and another pump is added. The removal event is reflected in the runtime model with history by the update of the DTS, the deletion timestamp of the pump that has been removed. So the pump is still reflected in the runtime model with history, but only its deletion timestamp has been updated. In that sense, the runtime model with history transcends the traditional notion of causal connection as I described it before, in that it reflects removed elements. Another important feature is that past snapshots are collectively reflected into the runtime model with history. That is, the top compartment sequence of graphs, GT, GT plus 1, and GT plus 3, are all reflected into the runtime model with history at time point t plus 3. Step 2 of InTempo concerns the scalable querying of the runtime model with history, which is the second requirement of the research objective. Queries of adaptation rules, I remind you that employ patterns, that is, structural fragments, and matches of these structural fragments in the runtime model with history constitute adaptation issues. Sometimes simple patterns are insufficient for more sophisticated structural requirements. I remind you the example from the medical guideline we discussed herein. If there is a procedure, a drug should have been administered 1 hour before. The patterns on the right, Q1 and Q2, represent structurally these requirements. Q1 associates a patient with a procedure, and Q2 associates the patient with a drug. However, the requirement of the real medical guideline also necessitates that a pattern is prohibited, which cannot be expressed with simple patterns. That's why queries are equipped with application conditions based on nested graph conditions. That is a language that supports first-order logic on graphs. It supports concepts such as conjunction, negation, and quantification of structures. And with these concepts, we can actually express such sophisticated requirements. For example, the example I mentioned before, here we require that if there exists a pattern Q1 in the runtime model with history, then it's not the case that Q2 doesn't exist. We also, of course, can capture this requirement by abbreviation of first-order logic, such as the implication. I remind you that here we talk about matches of these patterns, for example, Q1 or Q2, in the runtime model with history. NGCs, nested graph conditions, are highly expressive, but unable to natively capture temporal requirements, which is necessary for the second requirement of our research objective, that is, querying historical data. For the example we mentioned before, if there is a procedure, a drug should have been administered 1 hour before. The structural requirements, if there is a procedure and a drug should have been administered, can be captured by nested graph conditions, as we showed before with the implication. However, the temporal requirement 1 hour before cannot be natively captured. That's why InTempo relies on metric temporal graph conditions, which build on nested graph conditions and support temporal logic operators for patterns, such as once and for all new. With these operators, we can capture requirements such as for all new matches for Q1 in the runtime model with history, there exists once in the previous 60 minutes a match for the pattern Q2 in the runtime model with history. Metric temporal graph conditions reason over sequences of graphs, such as the one we saw before, the sequence GT, GT+1, and GT+3. For more efficient checks, however, the reference in 5 provides a formal framework for folding a sequence into a single graph. Here we do that already in the runtime model with history, as I explained before, and translating a metric temporal graph condition into a nested graph condition, that is a purely structural graph condition, where temporal requirements are captured by constraints over the creation and deletion timestamps in the runtime model with history. So based on ideas from the framework, we translate a metric temporal graph condition into a nested graph condition that can be checked incrementally over the runtime model with history. Just to visualize that, on the left, we have a metric temporal graph condition checked over a sequence, and we translate into an equivalent structural graph condition checked over a runtime model with history, where temporal requirements are captured by constraints over the creation and deletion timestamp in the runtime model with history, and where this is captured by gamma, and where SAT is a satisfaction check for these timing and attribute constraints. Step 3 of InTempo considers the sustainability of the runtime model with history, which is also the third requirement of the research objective. In runtime models with history, deleted elements from the system are not removed, and this can quickly render a runtime model with history impractical. In practice, domain-specific policies are used to discard obsolete data from such systems, such as the smart medical environment. For example, retention policies, publicly available retention policies, specify how long patient data is to be kept. In certain cases, however, such policies are too coarse and may impact performance as accumulated data, as the runtime model with history keeps accumulating data, which can hurt the query execution time. That's why analyzing the query, we derive a finer pruning policy that is a relevance window for each deleted element, after which it can be pruned without any side effects from the runtime model with history. For the example from the real medical guideline we have discussed so far, elements in the runtime model with history that could be matched by Q1, that is the pattern Q1, can be discarded immediately after they have been deleted, whereas elements that could be matched by Q2 have to be retained for 60 more minutes after the deletion, as this is the relevance window that they can be relevant for a query execution. Just to visualize the type of nodes we target with pruning policies in a runtime model with history, here you can see this pump that has set a deletion timestamp that has been removed from the physical system, and these type of nodes are checked against pruning policies to ascertain whether they can be removed or not. I now presented the 3 steps of InTempo, and I would like to now make a recap and position InTempo all the steps in the context of an adaptation loop. InTempo consists of step 1, which is about assigning timestamps on sensed data from the sensors and updating the runtime model with history. Step 2 translates a query based on metric temporal graph condition into a nested graph condition query, that is a structural query, where temporal requirements are captured over creation and deletion timestamps, attribute constraints, and it's executed. This query is executed during analysis. Then step 3 prunes the runtime model with history at the end of each MAPE, ensuring the sustainability of the model. We implemented InTempo for a specific case study. The goals of this case study was to prove the feasibility of our approach and to evaluate, based on the query execution time, how fast issues are detected. In this context, a match for a query, I remind the audience, constitute an adaptation issue, and we wanted to see how fast those adaptation issues were detected. Also, we wanted to assess the sustainability of our approach, as I aforementioned, which in this context is represented by the memory consumption of the runtime model with history. The case study consisted of a simulation of an envisioned smart medical environment, as the one I described in the introduction, where sensors sense data and report it, and smart devices such as an insulin pump, for example, take actions. We monitor a medical procedure from a real guideline, in a query of an event condition action form. Our proof of concept implementation relies on the Eclipse modeling framework, the OCL constraint checker, and the SDM pattern matcher. Also, our implementation enables incremental execution by virtue of the SDM pattern matcher. On our experimental setting, we generated synthetic log data for a period of 1 month. The log data consisted of events relevant to the medical procedure we have already discussed. The events were timestamped and concerned actions that were translated into patterns that were added to the runtime model with history. For example, at time point 5, there was an event that added a procedure to a patient, and this was translated into the structure you see on the right, a node of type patient associated to a node of type procedure. Elements lasted in the runtime model with history for 10 time points. That is, they were deleted 10 time points after their addition. We executed MAPE loops based on a predefined frequency, and each MAPE processed an approximately constant number of events. In total, 400,000 events were processed, which resulted into 800,000 elements added to the runtime model with history. Also, in total, 720 MAPEs were executed per simulation. We now present the results. We first implemented 2 variants of the querying scheme, in tempo with no pruning and in tempo plus with pruning. Each variant was evaluated separately. We first present the results for the memory consumption. On the x-axis, you can see the increasing simulation timestamp. As the simulation proceeds, the timestamp increases, and this is what is reflected on the x-axis. This also means that more events, and that is, more elements, are added to the runtime model with history as the simulation proceeds. In tempo, scales linearly with the size of the runtime model with history. In tempo plus, maintains a constant memory consumption as the simulation proceeds. This is thanks to pruning occurring after every MAPE execution. The same trend can be observed for the querying time, where in tempo, the execution time in tempo grows linearly with respect to the size of the model, and where in tempo plus maintains an almost constant execution time. To recap, in tempo plus has a constant memory consumption and execution time while handling an increasing load of events. However, it comes with other considerations. For example, it incurs a cost on the MAPE loop execution time, which for our experiments it was negligible, but it can be considerable in other experimental settings. And thus I conclude the presentation. I would like to remind you the research objective, which was to enable time and resource efficient adaptation that makes use of temporal data on the history of the system execution, and how we presented a scheme which enables storage of temporal data, which was the first requirement from the research objective. It does so by using runtime models with history. It also presents scalable querying for these runtime models with history, which was the second requirement from the research objective. And also it offers, in tempo, our scheme offers the capability to only retain data in the runtime model with history that is relevant to the queries that are being checked. That was the third requirement, keeping the runtime model with history resource efficient. We consider our work paves the way for history-aware self-adaptation. We are working on formalization of our approach, systematizing in tempo and supporting more complex case studies, automatically deriving a pruning policy, and also extensive evaluation and comparison with related tools. I briefly present now references for this presentation. And this is the end. Thank you very much for your attention.